Everybody. So today I'd like to present the research based on the work my previous researcher, Dr. Wang, and then my current researcher, Rahim, who's actually also attending it, on the bridge deck analysis using refined analysis method. And so this is actually the project we actually had the start of about a year and a half ago, and because of the change of the personnel, I actually had a delay on the project. So today I'm going to talk about the background of our research project, the overall objectives, and also the planned activities with the proposed task, the current research progress that we achieved, and some of the future plans on how we move forward. Now we have everybody on board on this project. All right, so part of the research was driven by the motivation considering the bridge life loads and truck volume these days have been increasing continuously since the 1960s. A lot of the truck loads and wheel configurations, they no longer reflect the modern trucks, considering some of our special vehicles in California and also the special hauling vehicles and emergency vehicles in the nation. The existing and new bridges, a lot of these bridges are actually prone to the loss of performance, considering fatigue and the cracking under high cycle loading fatigue itself, and caused by a lot of our daily traffic during their service lives. So this part of the bridge deck analysis method was based on the existing AASHTO LFD design specification. However, many of these methods recommended in the specification has restrictions and limitations. For example, the approximate method, even the refined method, actually that is lack of the guidance, and then the empirical method in the AASHTO specification is not even allowed in our California design. So the objectives of this research included the development of updated LIFD-based design method using the refined analysis methods. And we would like to incorporate the modern vehicle configurations, the dynamic loading condition, flexion shear demand into the refined analysis. And the other task in this project is to conduct a state-of-the-art review of the fatigue model itself for concrete bridge deck design and come up with a methodology for future consideration, since this task of this is actually slightly beyond what we can achieve in this 2-year project. So that was the scope of this particular task on the fatigue issue. So these are the planned tasks we actually targeted for this project here. And some of these have been completed. As I go through the presentation, you'll have a better idea. So we started with a finite element modeling of bridge decks. We started with some of the verifications of the existing model, and we completed the literature review on the fatigue model on concrete bridge design. And we went into the parametric study of the bridges and looked at the command database. And then the remaining tasks that we will go through are the qualitative assessment of the Approximate method and the recommendations on the future design right here. So the finite element modeling itself is a preferred method because a lot of the simplified strip method is conservative and less realistic. The two-dimensional grillage method and some other simplified method, they have inherent inaccuracy for many cases here. So what we actually targeted is a more refined method using the finite element method, picking one of the softwares in the existing literature using it's called Athena. The type of bridges we're considering is the casting place pre-stressed box girder type, and this which is our current focus. And we also have a plan of extending this into the precast pre-stressed eye girder case. The prototype bridge examples are selected from the existing Caltrans bridge example database, and we also have some independent verification planned in the future using other guidelines or manuals. So with the finite element model, as you can imagine, the three-dimensional analysis on an entire bridge, in considering all sorts of configuration, is something very challenging task. It is also causing a very much unrealistic workload of this modeling, which is oftentimes impractical in considering many of those configurations. So we actually spend quite a bit of time in configuring out a simplify or approximate method here using a rigid support model as an alternative to this particular three-dimensional refined model that actually considers all types of components. So it is trying to conservatively envelope the response and the results of a three-dimensional finite element model in order to provide a reliable but also representative cases for real bridges. So we had to narrow it down also on the focused parameters, and this is actually based on a parametric study in the existing bridge types that we have in the database. So this particular modeling strategy involves the part of the restraining of the girders from their vertical movement, but it is allowed to rotate freely with the pin support along the entire length of the bridge. We also had the vehicle HL93 truck loads considered. The current pressure of the tire is 100 PSI, and we also have a case to be included for the 125 PSI tire pressure, which is more current in the Caltrans design case. And there are some of the other loading cases we're considering in the transverse direction in order to obtain the maximum bending moment, positive and negative moment, including the shear, and then compare that with the final element refined model that actually includes all the components of the girders. So the two cases we picked is the one is the smaller box girder, which is actually about 38, 98, it's about 160 feet long. And then the total width of the bridge is 42 feet wide, about 4 cells in the box girder. The second case example we picked is a larger box girder in the database in California, which has about 400, 500, actually 750 feet of the span length, and also the total width of the bridge is about 70 feet in this particular. It's also a 4-cell box girder. So these two models were actually verified in our modeling at the very beginning, just to try to come up with some understanding how this behavior would look like. In the rigid support model, we actually use, for example, with this small box girder as an example, this is how we actually modeled this. At the bottom of the girder, we had the rigid support that the girders are allowed to rotate. However, it doesn't have any vertical movement. And in the transverse direction, we had the tire pressure with the two of the axial loads right here that moves transversely along the entire width of the bridge right here. So the small box girder actually had many cases. We varied the loading transversely with about 1.1 spacing of the girder in running all these different cases. Is about, you can tell it's about 20 different cases here. And then we yielded the most critical location where the load of the truck actually yields the largest positive bending moment, negative bending moment, and also the shear case. Same thing for the large box girder. We had the scenarios run across the entire cases here. And also in the span scenarios, in most of the Caltrans bridges, we actually had a discussion in identifying some of those most critical bridge cases in the Caltrans design cases. They have a lot of the 3 span bridges, 1 single span, 2 single span bridges, and we actually had the analysis based on the 2 identified critical scenarios to start with here. So the post-analysis actually extracted all these results, looking at the integrated moment along the inference area and also the shear case scenario. So this is what we actually was able to envelope in this rigid support model. And you can tell that the bar plots here is what we have using the refined model. So for example, the top left here is the average moment envelope, and then the red line and then the purple line is what we obtained from our rigid support model as an envelope capturing the behavior. And the right-hand side is the average moment at a different location, 0.75, 3/4 away from the span length, and then the shear demand at the bottom as well. So same thing, we had the extraction of the data for the large box girder, and then the conclusions we obtained here is some of the results. For example, for small box girder, the rigid support model actually yielded a slightly larger result in the maximum positive moment, somewhat larger maximum negative bending moment, and then the maximum shear is about 3.7% higher than the refined model. So for the larger box girder, we also had the similar conclusion. Towards the end of our analysis, we actually were able to convince ourselves that these differences are acceptable for what we actually need to achieve in the project right here using the rigid support model. So we also ran some verification cases of other scenarios, since originally we had to identify the critical scenario, but then we were also trying to verify this is okay for other cases in the analysis. So these are some other cases we actually verified. So there are some of the results in the verification process, and in, of course, the entire process, we actually have a slightly more conservative capturing using the rigid support model, which is actually not too bad for what we actually need to achieve here. So this task one was a major work that we did the verification of the rigid support model to conservatively replace the refined model with both the small and the larger box girder examples. And then the load demand could be influenced by the span arrangement, but we actually had several scenarios actually run across the cases. The results of the rigid support model actually were mostly larger than the refined model, but on the conservative side, it's still acceptable. So we're actually going to use that rigid support model for our production run in the next step. So in parallel to the next step, we also completed the literature review on the concrete fatigue model for bridge deck design. So this fatigue issue is a long-standing problem with most of our bridge design. On bridge decks, this is actually a more of an issue in the maintenance side. So what we see is a lot of the reduction of the concrete stiffness, the increase of the deflection, and also the pre-stress loss, a lot of the reduction of the natural frequency due to the fatigue loading. In most of the design codes, this fatigue issue is not well captured due to many complicated natures of this fatigue issue itself, and also the time-consuming experimental work that would be required for this issue. So in the summary of this literature review, we captured most of the material level degradation in the concrete under fatigue, but most importantly is the structural level degradation in the concrete bridge decks. The gradual increase in the deflection accompanied by the decreasing deck stiffness is something very common. There are also punching shear failure modes with different types of cracking pattern observed in the experimental work for both fixed pulsating load or the moving wheel loads. And also due to the limited research, a lot of these models are based on their own empirical results, so it's still not very reliable for the design purpose. And then the existing representative models that's available in the literature, including punching shear models, yield line theory, and some of the semi-empirical fatigue models. So some of the research also conducted a finite element modeling strategy to actually understand the failure mechanism, which can be extended to the current database if the computational effort is acceptable. So in conclusion of this task, we actually recommended two practical approaches using the existing data to estimate the fatigue life of bridge deck. One of them is a stress-based method that's actually looking at the concrete stress level in the material level and look at the failure plan of the punching shear model. And you can combine it with analytical or numerical method to estimate the fatigue life of a bridge deck with the material level models. The other one is the force-based method. We actually provided a strategic plan for this, which includes the load carrying capacity estimate and also the punching shear failure of the concrete slab, and we look at the critical vehicle load applied to estimate the fatigue life. So this is more of a structural level model itself. I have more information related to this, but I think before I run out of time, I'm going to move to the next step, which is our planned task. So this parametric study is actually very critical for our production run of this particular research project here. As you can understand, in the existing bridges, there are many factors that's influencing the behavior of the bridge, the span length of the bridge, the number of bridge spans. Then you also have the number of girders and design lengths, overhang width. All of these are complicated issues on the bridge itself, and which some of them are more so for certain type of bridges. So in the beginning of this task, we actually collected the 120 plus bridges in the Caltrans database across California, looked at the correlation between some of these parameters. Not all of them are possible since the cases are dependent on their own scenario. So we looked at those ranges of the parameters, the span length, the girder spacing, the deck thickness, and also the overhang, the number of the box girder cells, and come up with some of the regression analysis as much as possible. But some of these were actually not feasible due to the interference of some of the parameters. So to have a short summary of this, the change of the girder depths can significantly affect the load demands of the deck design. So the frame action in the box girder has to be considered to yield the most accurate results. Now, the cross slope is another interesting aspect. It also has a positive influence on the load demand of bridge deck. However, in our analysis, we're going to actually neglect this effect since the set of the database for small cross slope between 1.5 and 2 degrees is not as significant. And then the length of the inference area is also something across this study. We were able to narrow it down to be 20 feet in the inference area. And this is also the approximate size of the punching shear failure boundary for the conservative design. And then for the end, we also narrowed the parameters to the girder spacing, the depth of the girder, the number of cells for the production run using the verified rigid support model. So this is the matrix for our next step production run, which is still undergoing right now. We have identified these types of bridge cases with the spacing and the number of cells, and then the thickness of the bridge based on the previous Caltrans deck design. This is actually has been updated to the latest one. We have to adhere to the newer design recommendation at Caltrans. And there are also some of the other parameters we have here. So this is part of our plan for the next step. But of course, along the process, we will be using the 3-dimensional refinement analysis to verify some of these models. And the other part of the task is to do a comparison or the assessment of the AASHTO Appendix A4 design using our analysis result to see how conservative or approximate the other method is leading us to. And then we also have some other cases we're going to consider with the P15 loading scenario that the pressure of the tile are upgraded to 125 PSI. And then we have a few other cases that we're going to run for the eye girders. If time commits, we will also include other type of vehicle types, such as the emergency vehicle and the special hauling vehicle. Okay, so this is a part of our plan moving forward. And then the remaining tasks for the rest of the project, including assessment of the Approximate method, and then also the design recommendation. So the assessment of the Approximate method is part of the task related to the AASHTO design that we've been using for many years. And we actually wanted to make sure that the method is still valid in what we wanted to verify here. And that is basically, I think, all the tasks we planned. And I would like to thank my previous researcher who actually left the project, but he actually provided the majority of the slides on this part of the presentation. And I will conclude with this for further questions from the audience. Thank you.
Okay. Any questions for Professor Cheng? Maybe you can go right there. Yeah. That's good.
Okay, hello. So I'm not familiar with what the P15 truck is, but is that like a single trip permit or continuous trip permit, or what type? HL93 is a standard design truck, but then what's P15?
The P15 is our Caltrans permit vehicle. So it has 15 axles of the truckloads spaced at certain distance. And it's actually very special in Caltrans, in California, not in other states. So we have this particular loading. I think I probably have a slide showing the layout of this truckload in the loading case at the bottom. So the P15 looks something like I think it looks something like this one here. Oh, right here. So this is actually what we have called as a P15 truck in Caltrans. As you can tell that it has all these patch loads lined up consecutively next to each other, 15-foot kip, and then they're 18 feet apart, spaced out.
Okay, good. Yeah, HL 93 is just a design
Correct.
truck. This is an overload, I guess. So, yeah. Okay, thank you.
You're welcome.